Okay, in this video we're going to talk about ways in which we can maximize our power area, right? 1 minus beta. And I'm going to do it continuing our discussion using these graphical representations of the null hypothesis and the alternative hypothesis as these Gaussian distributions with our various areas, right? Alpha, 1 minus alpha, beta, which would be this blue area under the blue curve here to the left of our decision rule, our alpha level, and 1 minus beta to the right of this. So we want to maximize this 1 minus beta region. And so I'm going to use these graphs, and we'll talk about the different ways we can do that. So you have those handy. I put them in the paint, and I'm going to start with the easiest one. It's the one I started with. One of the ways we can increase power is to increase our alpha level. So here I've shown you, and this is where the numbers are meaningful. So I'll put the null hypothesis here with a mean of about 70, right? And the alternate has a mean of about 130 or so. So you can see those distributions relatively. The numbers don't mean anything by themselves, but they show you a relative difference here. And here it is with the alpha of 0.05. So that means that this area here is, encompasses 0.05, or really 0.025 in this tail, 0.05 in this tail. And you can see where the criterion, the line is placed. And so this region right here, I'll draw on it with a brush. This region right in here, right? This region right in here is our beta region, and the area that we want to maximize would be this area out here, right? The 1 minus beta region. So now let's look and see what happens when we increase our alpha. We double it from 0.05 to 0.1, and you'll see that this criterion line moves from here to there, and so that makes this entire region much bigger. Our 1 minus beta region gets bigger. And it's true. If you increase your alpha, right, you're more likely to reject the null hypothesis. And what must you do to have a correct decision of 1 minus beta or power? Reject the null hypothesis. So that's how they're related. But also remember that what this does is this increases your probability of a type 1 error. So that's not a desirable way to do it. But it could be, and we'll talk about in class like when that might be, or maybe you could think about when that might be, when you might have research situations where that might be a good solution. But generally, it's not a good solution. So there's other solutions that we can do, and one thing we can do is that we can decrease the sampling distribution variance. So here's our graph that we're starting with, and what I've done is all I did, everything's the same, the mean value is the same and everything, but I've changed the variance here, changed the variability for these theoretical distributions that were created. So the mean value is the same, but they're skinnier, right? And as they're skinnier, and the criteria, you'll see the criterion here still at 0.05, so this area under here is 0.05, but it shifts backwards, right? And you'll notice that this area here, compare this area here, right, to the right of the line, but belonging to the blue curve, right, with this area here, to the right of the line belonging to the, so there's a greater area, right? That's our 1 minus beta region. And that area is bigger when we make our sampling distribution variability smaller. Well, how do we do that? Well, remember what we're using to estimate the sampling distribution variability. We're using the variability from our experimental groups. So if we improve our precision with our experiment, our measurement precision, decrease unwanted variables, we'll get a better estimate of the sampling distribution variability. The tighter experimental control will cause a decrease in our sampling distribution variability estimate, right? So that's another way to do that. Another way to do this also is also remember our measure here is standard error of the mean, right? So one thing we can do that I just mentioned, we can decrease our experimental variability by controlling variables. The other thing we can do is increase n, and that will also do the same thing by shrinking our sampling distribution variance. So one easy way to increase power is to add more subjects, collect more data, and that's often a thing to do. But I would argue that this is a better way. You control those unwanted variables, you improve your measurement, improve your experimental paradigm in some way, shape, or form. That's much more preferred over just collecting more data. Now, the last thing that we can do to maximize power is increase our effect size. Now, this is not something you can do once you've already started a study, but we decide the levels of our IV. So increasing the effect size means using the largest level of the IV that you can, that you're comfortable with. And so my professor always described it as you could measure behavior and you could hit people over the head with a feather. That would be a weak IV, or you could measure behavior and you could hit people over the head with a hammer. That'd be a much stronger IV. And so the idea is use the strongest IV possible to maximize your effect size. And let's look at, this is what our distributions would be. And if you're changing the effect size, what you're doing is you're making the differences more apparent and you're pushing the distributions a little further apart, right? And so the blue distribution and the red distribution have less overlap because the magnitude is greater of the independent variable. And when you push these distributions, you increase your signal, if you will. If you push these distributions further apart, this 1 minus beta region gets bigger. So those are ways to maximize power. Hopefully, you not only understand statistically how to maximize power, but you sort of have an idea graphically of how that would